Everyone, and welcome to today's webinar, Off the Grid, Advanced Scanning Strategies for Modern STEM. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We'll attempt to answer any questions for the speakers at the end of the presentation. If we don't get to your question, we'll follow up via email after the webinar. Now I'd like to introduce the speakers for today's webinar. Stephanie Ribet is a staff scientist at the National Center for Electron Microscopy in the Molecular Foundry at Lawrence Berkeley National Laboratory. She runs a research group and user program focused on the computational and experimental development of multi-dimensional electron microscopy methods with an emphasis on cryo approaches. Shelley Conroy is an associate professor in functional thin films and microscopy and Royal Society Tata University Research Fellow at Imperial College London. She runs a research group focused on in situ microscopy hardware and software technique development and thin film growth of materials for energy, semiconductor, and quantum technology applications. Her European Research Council COG DISCO grant uses advanced in situ TEM to probe emergent magnetic phases at polar interfaces during electrical biasing and cooling to helium temperatures. Shelley is also a principal researcher in TEM at the Tyndall National Institute in Ireland, supporting the development of the new microscope suite, and is co-director of the Center for Doctoral Training in Royce Materials 4.0 in the UK. Our third speaker, Mariana Palos, is a PhD student whose research explores dynamically induced charges in polar order and domain wall dynamics in non-classic ferroelectric thin films. Using advanced electron microscopy methods, including 4D STEM, she investigates how beam material interactions can reveal nanoscale functionality in complex oxides and borosites. Now over to Shelley.
Thank you so much, and thank you for the introduction and the invitation for us to present. I'm really also very happy I get to do this with Stephanie and Mariana. So I'm going to just start the presentation, and then it'll be over to Stephanie, and then it'll be to Mariana, and then back to me. Where we're based is at Imperial Centre for Cryomicroscopy of Materials at Imperial College London, and we have a unique suite of facilities where our core, mission is to take materials that are beam sensitive, air sensitive, a lot of times looking at liquid solid interfaces, and we've built up a unique national facility there where we can bring our samples between wonderful electron microscopes and also SIMS and atom probe itself. And then within my research group, we've the past 5 years been working on looking at materials down to very liquid nitrogen temperatures, but staying at atomic resolution, and working with Gatan to automate a lot of that in situ data, including 4D STEM and EELs. And then more recently, and actually just this morning, which is very exciting for Mariana as well, is that we've been working on helium-cooled electron microscopy, spectroscopy, and 4D STEM as well. So this is my wonderful group. I'm very lucky, and within also the within Imperial, we have many electron microscopes and FIBs and atom probe, and also we have what I believe is the highest SEM FIB in the world, because it's on the 8th floor of a building which you're not supposed to put microscopes on. But we also have Gatan cameras there for EBSD, which we're also very lucky to have because we have many pixelated detectors also within inside the SEM. And now what I want to just quickly talk about at the very start, because it's always nice to talk about the history of electron microscopy, was that actually Gatan was one of the founders, Professor Peter Swan, actually started Imperial Materials, and I was lucky to get some very wonderful PhD students from him back in the day, where we had a reunion when we opened our center. And then Professor Grace Burke actually sent me on some examples of even before they had Photoshop, where they had Peter Swan inside and one of the original in situ holders, and this one was actually the helium holder that they designed back in the early 70s. So with that, I'm going to pass on to Stephanie.
Awesome. I hope you can hear me, and thank you all again for coming. We're very happy to share with you some of our work today. So briefly, I wanted to tell you a little bit about the center where I work. This is the National Center for Electron Microscopy, which is part of the Molecular Foundry. The Molecular Foundry has expertise in lots of areas spanning synthesis, characterization, and theory. And NSEM, we specifically focus, of course, in electron microscopy. And we do research in a lot of different areas, spanning different applications of science engineering, especially focused on material science. What's exciting for me is we're actually expanding. So we'll have some new instruments going in a new building, and this is very focused on new tools for cryo-electron microscopy. It is free to use our center because we are a user proposal center. And we have, the way you access our center is through user proposals. We do this twice a year, and we actually have a call open now. So if anyone is interested in coming to MSEM and doing some research with us, feel free to reach out and send me an email. My email is here. So without further ado, I'd like to go ahead and start the presentation and dive into kind of what we want to talk about today, and starting with some introduction and background to why we really care about doing these types of experiments. So I imagine that many people on the call are familiar with scanning transmission electron microscopy, or STEM. And specifically, we think a lot about this as a very useful tool for doing all kinds of material science characterization. With our STEM probe, we have a very small beam. Depending on the alignment, this can be a sub-angstrom probe even, or often we want to use this more on the nanometer scale. So you get very high resolution, and you can collect all kinds of different modalities at the same time. And you'll see these throughout the presentation. So for example, you can do imaging. You see this in the gold nanoparticles you're seeing in this first image on the left. This is nice because we can know about the morphology of your sample. You can do diffraction, and this is very position-sensitive structural information. Another technique that will come up a lot today is 4D STEM. This is position-sensitive structural information. So as you scan your beam across the sample in Rx and Ry, at each position you collect a diffraction pattern. So you end up with, it's called 4D STEM because you end up with 2 dimensions in real space and 2 dimensions in reciprocal space, and you can study how materials change on a very small scale. So this diffraction pattern here is from a study mapping strain in silicon materials, and we can get very high resolution with this. You also can do spectroscopy, both EDS and EELs. I'm showing an EEL spectrum here, which can tell you all kinds of things, but of course, nominally about the composition of your materials. And then lastly, what's amazing is you can do all this in situ. So you can study how materials change under the electron beam. This includes with introducing all kinds of external stimuli, such as heating, cooling, biasing. And you can see in this example here how these gold nanoparticles change, and you can do atomic resolution imaging with these in situ experiments. So I want to introduce you on the next slide to one specific flavor of 4D STEM, which is phase retrieval. And maybe you've heard of phase retrieval or ptychography. This is something that we're going to be using in this presentation today. And in general, all these different techniques try to solve what's called the phase problem. The way the phase problem kind of, the problem itself, this is not just for electron microscopy, is that we have some initial probe, which is a complex wave function, and it interacts with our sample. And specifically for a lot of weakly scattering samples, a lot of the structural information we're after is unfortunately encoded in the phase of this transmission function, so that's such that we have a phase modulation on our exit wave, and this is a problem for us because our detectors are recording the intensity. So this phase information is lost. Luckily, there are a number of approaches to retrieve the phase of our sample, and this allows us a lot of benefits, including dose-efficient characterization. It allows us to image the weakly scattering signals, and also encoded in this diffraction pattern is actually some 3-dimensional information. So we can recover some depth information about our sample, and 4D STEM is what allows us to be able to do this sort of phase retrieval in STEM. On the next slide, there's a number of ways that you can recover the phase of your sample with 4D STEM. So this is an example. This is a twisted bilayer of MOS2. Compared to the dark field imaging, all 3 of these other phase retrieval techniques perform much better. Higher signal to noise, you can see much more clearly what's going on. There's a number of approaches you can do this. So the first here is differential phase contrast, or DPC. Next to it, we have parallax, or tilt-corrected bright field. And I would also put SSB and direct ptychography in this sort of bucket as well. And then lastly, at the end, we have iterative ptychography. And what's nice is these methods are all different. They have sort of different computational approaches that you use them, and they lend themselves to different types of applications. And so it's great that we have different methods. These specific ones are written. This code is from Py40STEM. And in the next slide, it's a little bit more information. So we have in Py40STEM a lot of open source code, as well as tutorials, and then some more background methods about these techniques in the paper linked at the bottom. And also this article here, this is an elemental microscopy. So this is an interactive journal that'll tell you more specifically about this tilt-corrected bright field stem. We are actually also working on some new code. So this is Py40STEM, but look out for Quantium. This is an ML-based approach with a lot of ptychography tools. So to give you a little bit more sense about ptychography, this is specifically the phase retrieval technique we're using in this presentation. This is an iterative approach. You start with a guess for your initial probe and sample potential. You have some forward model that allows you to compare this guess to your experimental diffraction patterns, and then you update. And you're doing this over and over and over again for many probe positions, for many iterations. And this gives you a number of advantages. First, you can do aberration correction, so you solve for your probe and you can deconvolve this from your diffraction data. And one thing you can also do is what's called super resolution. So you can move beyond the sort of 2 alpha limit that you might be familiar with dark field imaging. So on the next slide, I have just one very brief example of the power of ptychography. Shelley, if you don't mind switching. To the next slide. This is an example. This is work led by Frances Allen at UC Berkeley, where she's using, the ion beam and the electron beam for inducing defects in materials, and we want to study them with electron microscopy. And if we look at this few layer HBM sample, it's very hard to get a nice image with dark field imaging because it's so weakly scattering. This will depend, of course, on your electron microscope and the sample. But with ptychography, for a similar dose from a different field of view from the same sample, we get a much higher signal-to-noise reconstruction, we get higher resolution, and now we can pick out large defects as well as atomic defects. So this is really the power of ptychography, and we'll be doing this in the presentation today. So now on the next slide, I want to introduce something else, which is actually why we care about smart scanning and why we do this sort of adaptive scanning. So conventionally in electron microscopy, we do what's shown here on the right panel. This upper left image is A, where you do what's called raster scanning. So you go across a row and then you fly back or jump back to the next row. But there's been some really interesting studies recently that have highlighted the limitations of this. So one thing is doing these sort of alternating scanning type approaches has been for many samples shown to reduce damage. So for the same amount of dose, you can get higher signal to noise data. This also lends itself not just for imaging, but spectroscopy as well. And then lastly, if you think about this ptychography algorithm I just introduced in the last slide, to be able to converge this, you need to have first overlap between your probe positions in real space, as well as really precise control and understanding of where your beam is. So if you think about kind of having more control of your electron beam through adaptive scanning, this gives us another handle to do electron ptychography. And then I also wanted to point out that this kind of links into all sorts of other hardware and software advances in the field of electron microscopy, everything including electron counting, drift detection, compressive sensing, faster cameras, ultra-fast beam blinkers. All of these sort of go hand in hand with when we think about doing this smart scanning. And then on the next slide is kind of one other specific example. So we know that the electron beam can have a profound effect on materials. This is both a benefit and a detriment. And people actually really cleverly use this for controlling materials under the electron beam with in situ experiments as well as sculpting and driving samples. So using the electron beam to sort of synthesize materials. And now if you have the ability to really write the electron beam and control it, you can think about synthesizing structures even atom by atom and really using the electron microscope tool as sort of a almost synthesis or materials control or another way to control in situ experiments. And this also links into our improved ability to use the electron microscope. More and more we're able to do studies where we can actually see individual atoms, study the structure change in these materials. So this is sort of linked to other advancements going on in the field. So let me show you on the next slide, specifically kind of the different scanning protocols we use in this study that we're going to be telling you about today. So in the upper left, you have this conventional raster scan where, as I mentioned before, you have go across the line and you have this flyback. There's spiral scanning, which is a nice way to avoid this flybacks, as well as these sort of interleaving scans where you're doing multipass and going to different positions. And in general, I hope you take away from this is this certainly is a way of changing the way you do your experiments, but it also really gives us an amazing handle for adjusting how we do experiments, what the dose is, how we do drift, how we do different types of reconstructions for 4D stem and eels. And that's what this presentation really is about today is, there's not one best scan strategy, but being able to have this control allows us to change and think about how we do electron microscopy. So our approach is shown on this next slide here. We specifically want to think about improving signal to noise, improving experiments for challenging materials, not just for model systems, and doing this for low dose techniques, combining this with other things. So we program our scan. We're going to show you in this presentation today some dark field imaging, as well as 4D stem ptychography reconstructions, as well as eel spectroscopy, and then also how this links with other types of experimental strategies. So on the next slide, you can see, sorry, waiting for the next slide, how we actually do this. This is implemented in Gatan. It's pretty straightforward. This has been well integrated in the software, and this gives us sort of the way in which we are able to control the scan pattern with custom scanning or scripting. So now I'm going to pass it over to Mariana. She is going to go on to the next section and tell you a little bit more about some of our results with these different scan patterns.
Thank you, Steph, for the introduction and some background in all the ways we can use a beam in STEM. So I'm going to show you some results in some ways we've used these different scan patterns that, as Steph showed now, you can now have in Gatan, and they're very accessible. So this is just an example of how a custom scan looks like. On the top, we have a spiral scan, and on the bottom, we have a scripted one where you can use Python code to just design your own script in Gatan as well. And these are just examples of ADF and EELS data, all acquired without drift correction and no subscan, so that we can actually compare and test how changing the beam path affects imaging and spectroscopy quality. So if we go to the next slide. Because this is all relatively new with the electron beam, we want to test how does the different scan patterns affect the ADF signal as well as spectroscopy. So we did this test. So we chose DSO as a base to sort of benchmark these interactions. And we did it across different scan patterns. So we have normal, random scan, skipping pixels and sequential and different spirals. And we can see that there are some visible discontinuities in some of the ADF images from different scans, especially for large pixel jumps, as we can see here in n equals 4. So the bigger the probe jump, the bigger the artifacts, or the more artifacts we were getting. And as Steph mentioned, all of these techniques are very sensitive to knowing exactly where your beam is and the scan direction. So we can see that having these pixel jumps and having pixel jumps that get closer to your interatomic spacing can introduce a lot of artifacts. And if we compare it to a more smooth scan on the right, for example, spiral, that one we obtained signal that was closer to the raster scan that we can compare here. So if we see, this is a very brief, like quick line profile from it, we can also see that we get some reduced peak intensities in the bigger and sequential scans, or the bigger jumps, whereas spirals show a better or more comparable signal to raster. So if we go to the next slide. Okay, so because we're testing all these different scans, we care about drift as well. So we compared the drift trajectory for the same scans as before. And we can also see that for spirals and low-end sequentials, there's some enhanced drift correction here. So if we look at the plots here, so spiral in and spiral out, as well as n equals 2, so skipping every 2 pixels or 2 pass scan, we get less drift. And for high-end sequentials or bigger probe jumps, such as random, this gets worse. So, sorry. Oh, wait, sorry, can you go back? Okay. Yeah, so these were some just some initial tests that we did on DSO, as I was mentioning, but it would be really interesting to optimize this and really test the different drift rate for these different scans, especially for more beam sensitive materials as well. So these are just alternatives where we can see that having a more continuous probe trajectory without any flyback times or probe settling times could possibly improve drift here. And having analyzed ADF and eels, we now move on to 4D STEM. And again, this is an example of how the 4D STEM scan looks like. It's pretty similar to ADF. This is a 2x2 scan pattern, and this is a 4D STEM acquisition here. This one was done on a PTO sample. And I think the video is quite slow, but if you click the next. Okay, yeah. So we can see that using a different pattern, in this case, n sequential, we get this probe settling artifacts in our ADF images, both the parallel one acquired with eels and the virtual imaging. But with ptychography, we can see that we can sort of fix these artifacts. So as Steph mentioned, is all of these different scans can be tailored for different experiments, and there is no perfect or ideal scan. So using skipping pixels can improve in some data acquisition, in this case 4D STEM, while it can be detrimental in other kinds of experiments as well. So again, we wanted to test different scan patterns, this time with 4D STEM. So we did some ptychographic reconstructions. And again, we know that ptychography is very dependent on the position of the probe, and you want your probe positions to overlap. And for this, we realized that as long as the probe overlap is enough, you can still get a pretty good phase retrieval with, in this case, multi-slice electron ptychography reconstructions. And we tested this for different pixel jumps, in this case, n equals 2, 4, and 8. And under the same acquisition conditions and same reconstruction conditions, this ptychographic reconstructions were done with Pi4D STEM. We realized that there's not a lot of change in the lateral resolution for same parameters, but bigger pixel jumps. And we could see earlier from the ADF and EOS acquisition that the bigger the jumps, the more artifacts you're introducing to your ADF. But in this case, ptychography was really good at still resolving or getting very comparable results for different pixel jumps. So if we go to the, oh, thanks. So we tested it so far on DSO, which was our base material, in order to be able to compare and benchmark these different scan patterns. But we want to be using them as well in more sensitive samples. So we tested this on a barium titanate freestanding membrane. And this is a very interesting material because it goes through different phase transitions at low temperatures. So we wanted to do these experiments under cryo conditions, but as we know, cryo conditions can add extra challenges. So we can get more mechanical instabilities just from instrumental and holders. We can get increased drift as well. So if we see the HADF here on the left, this is like an unprocessed image, just as is under cryo conditions, and we can really see the artifacts coming from the cryo experiment. So we did experiments for this freestanding membrane, and we took some Tycho data under raster, scan trajectories, as well as spiral, and some different n-sequential scans. And none of the n-sequential scans or pixel jump scans reconstructed as nicely. But if we compare a raster to a spiral scan, we can see that the spiral scan really outperformed the resolution of raster here. And we can really resolve the oxygen if we look at the bottom right panel in spiral outwards. So we get clear resolution of the oxygen columns, even without drift correction. If we go to the next slide. And as I was saying before, this is really interesting because in BTO, when we're in the low temperature phase transition, we get this octahedral shift of the oxygen. And if we can really map that, we can track that. If we can really track the displacement of these atoms, we can test if this is really the ferroelectric phase that we're looking at. So from our experiments, some brief conclusions on how scan trajectories interact with Tycho. From that BTO multi-slice reconstruction specifically, we can see that even though with Ptychography, as long as there is enough good overlap, we can get good reconstruction. There's many other acquisition parameters that are relevant as well. But we can see that having a smooth scan trajectory that has no flyback or line-by-line effects, we can get a better or a more uniform probe overlap grid. And this is why we can keep the resolution or really push this reconstruction even further. And this is not the first time we see this. There's a lot of work that has already been done in non-raster scans in Ptychography with optical Ptychography and X-ray Ptychography, where they show that smoother trajectories can really improve the sampling uniformity. But now we're able to do this with electron microscopy as well, because we have all these new detectors and new techniques, faster cameras, and now we can actually test it.
Okay, thanks, Mariana, and thanks, Stephanie. I'm going to take over for the end. So Stephanie mentioned at the start of the talk, we're also using the different programmable scans, not just to see, I guess, what we're how that affects our samples. So for some beam sensitive samples, it certainly helps reduce the damage if we change our beam scan patterns. But also in other materials, for example, some 2D materials where you have different atoms inside them, you can actually move those atoms around, like some really beautiful work done by Dr. Thomas Suzy. But for us, we actually look at these for electric domain walls, and that's a huge part of Mariana's PhD. And so here, if people don't have background in it, instead of where you have a different atom or an interface where there's a change in the chemical composition, it's actually homogeneous. And what happens at the interface itself is that it's just a slight change in the location of the atoms within the unit cell. And then at those locations, we get changes in electronic, magnetic properties, and a lot of the times optoelectronic. And the cool thing about it is, though, is that what we want to do is design these devices, and it's a really big part of many actual semiconductor companies, where we want to move past fixed components of hardware. And so instead of making your hardware in the clean room and then that's it, you can't move actually where the functional interface is. In the case of these materials, that you can actually inject the functional regions, these interfaces that have changed in, let's say, conductivity or magnetism, and you can inject it or you can draw it like an Etch-a-Sketch, but you can move past an Etch-a-Sketch. You can also move them around. So this is where we just are applying a bias under light microscope, and you can actually move these interfaces back and forth. There's a lot of beautiful theory and work done on this, where other groups have shown that, in fact, as you move these walls, you can think of them like an avalanche, and then the movement is actually not so smooth. You can, under light microscopy, you don't really see this, but once you get to even low magnification TM, hopefully you can see that in that in situ video, there's this kind of slow movement and restructuring of the wall as it moves. So it's very similar to an avalanche itself. And yeah, and then one of the other things is that actually a lot of theory, again, work has been done where we, in fact, to get other functional properties like magnetism in a material that, in fact, has no magnetic properties, only as the wall is moving. And so we could take some materials that are sustainable, that we don't have issues with, let's say, mining cobalt or anything like that, and we in fact get magnetic properties just at the wall or the functional interface itself for these devices. Okay, so I've talked a lot about that, but we were really only at the start, and that's why we got lucky. That's also funding Mariana's work as well, where we were able to really probe this and see experimentally, can we pick this up? So we started a lot of this work a couple of years ago, where we did light microscopy, SEM. Back then, I couldn't move the electron probe around in different directions. All I could do was rotate the scanning probe direction, as most people know on this in this webinar. So if I moved my SEM and my electron probe in the SEM around, I in fact got many different types of patterns that were not known before. And other groups as well followed this, and they've shown that in other materials they can see this as well. So we already knew that if we moved our electron beam position around relative to where the domains and the walls were, so these interfaces, we in fact could get very different patterns. So we knew there was something interesting happening there. Then we took these samples and we looked at them inside the transmission electron microscope. So we moved from the SEM into the STEM. And we could see even from just moving again the scan direction, so just rotating it by 90, we could again see that the exact same area, we're getting very different patterns from the domains and how they actually in fact move as well. We could even pick up a certain domain wall, which I'll show you in a second from 47, where we could see that in fact the wall, we can move it out like an accordion, and depending on the electron beam direction, the scan direction, we could expand it out like an accordion, and then we could push it back together again, and it was completely cyclical. So we wanted to understand what was happening. And then in fact, this was our start of our wonderful collaboration at NSEM several years ago now, where we started looking at 40 STEM and using this to actually map out also the change in the strain tensors as well. And so for us, we were looking at our the EXY, and then basically seeing like how that changes. And what we could see already, which was very interesting, was that far away from even the wall, the domains themselves, the strain was very much changing. And in addition to that, also the polarization, which I'll show you in a second. So it's really important for us to think about, at least in all the systems we've looked at, these ferroelectric systems, how we're actually scanning our probe when we're doing these in situ experiments. And also even when we're not doing those in situ experiments, when we didn't think we were moving something, in fact, we are changing things. Okay, so I've shown you the light microscope where we had these walls moving. And then in the middle, we have the DPC, the STEM. And then what we did more recently now is well, let's actually use all these cool scan patterns and see what we can do with these domain, the resulting domain patterns themselves. So I'm just going to show you some initial work that Mariana, has done, where she was using different spiral scan patterns and then collecting 4D STEM, and then actually mapping out the change in the polarization within the different domain patterns that we have. And we can show very clearly that the domain patterns actually change significantly depending on our different scan directions. We take, of course, our 4D STEM because we haven't really shown this in specifically in this presentation, but so basically we take different positions. We can see that in different domain locations that we have different polarization vectors. So whether it's up, down, left, or right, and we can map all that pixel by pixel. And then what we can see then is the different domains that we're actually getting. So let's say we have polarization up in one domain versus down in another, or left or right. And we investigated basically how those domain patterns are affected by the different scan patterns. We could see this before, as I said previously, where if we just rotated the scan, that they were in fact moving in different directions. But this now is allowing us to change our scan pattern directions and in fact make very different types of walls and interfaces. So we can already see what we're forming now are these vertex patterns that we hadn't seen before, and we're trying different types of scanning directions as well to hopefully induce more chirality in these domains. So then from that, as anyone that knows it takes 4D STEM data, once you take that, it takes a really long time to process it. And so we applied some machine learning approaches, and where Finn in my group has been able to now map out basically the different polarization directions much quicker. So we've gone from, in our case, sometimes those data sets are really, really heavy, and it goes from several terabytes. And he's gone from hours now down to seconds in many of the cases. And then I just showed you one material system all at room temperature, but we're investigating many different systems. So if we go back to barium titanate, that classic ferroelectric system that Mariana had shown for the Ptychography, we actually can see that the different domain pattern, the different domain patterns that evolve as the stem is moving these domains at cryogenic temperatures, because again, in certain material systems, in fact, the interesting phases are at lower temperatures. So for barium titanate, we know that we get very interesting domain walls and domain patterns at these lower temperatures. So we wanted to understand what was happening. We took just a ELSA Gatan cryo holder. We took our barium titanate single crystal, so not a freestanding material. And then we just kept scanning. Mariana and me had a lot of fun making different patterns. But then what we wanted to do, of course, was now let's change the different scan directions. So in this case, we took 4D STEM, not just STEM. We did the raster pattern, and then we changed that to the spiral scan pattern. And then these are just virtual dark field images we got from our 4D STEM pattern that we got at each pixel. And then what we can see is that we in fact get very different patterns depending on the scan direction again. And so what we want to do with all of this is we really want to program this in and embed it, not just looking at really cool stuff, but we're right at the start right now. And so what where we've come at the start from is that we knew that if we moved our STEM probe in different directions using classic, just rotating the scan direction, we already knew that we could move these domain patterns. You can see in the atomic resolution video at the very bottom of that same material that we can actually map this atomically as well, that motion. But until very recently, working in collaboration with Liam Spillane at Gatan, now we can actually move the electron beam in loads of different directions. So it's wonderful in one case for changing the different scan patterns to avoid beam damage, but also for us, for our research, at least within Imperial, we want to look as well at how we're changing the different ferroelectric, ferromagnetic domains using different scan trajectories. So if we think of those practical considerations, so we choose a scan strategy depends really on the material sensitivity. So perhaps the spiral scan is actually not the best, right, for certain materials. In fact, maybe in that case, it's much better to use something like a random pattern or some sequential more jumps because perhaps you don't need to be at atomic resolution, for example. And then we need to also think about the desired signal. So what is more important? So ADF versus 40STEM versus yields, because we can already see that there's a different effect on those, different types of techniques, depending on the different type of scan and strategy. We also need to think about the probe overlap as well. So when we're thinking that's very different for ptychography versus 40STEM ptychography versus, let's say, 40STEM, where I just showed you where we were doing polarization, so much lower convergence angle. So let's say we're doing strain or polarization mapping, then we really need to think about the probe overlap in a very different way. And then also really thinking about the flyback time, because even with the work we've done so far, we're really thinking about, okay, we can do a different scan pattern, but where is that probe actually ending up, right, after each scan? And then cryo versus room temperature. So, so Mariana showed barium titanate, and that's again where we were just using a traditional side entry single tilt, in our case, ELSA holder, right? So nothing fancy. And we really can see it really helps using different scan patterns for ptychography. And it also we also show that in fact ptychography in this case actually really helps. We didn't think it would be, because a lot of the times when we collect that data set, it's much slower than STEM, but in fact you're getting much nicer data. And then also, are you imaging or stimulating basically? So are we doing something where we're taking a sample and we don't want to change anything? That would be a very different scan strategy versus something like I showed you with those domain walls, or for example, many people looking at again 2Ds like the work of Thomas Suzy, where you're looking at these different atoms within inside the lattice and you want to see where they move around within the 2D material. That's very different than just trying to avoid damage, of course. So when we're thinking about all this again, so when is each scan useful? So Steph said at the start, so basically there's no perfect scenario. So we see that if we have a stable bulk sample, conventional imaging workflows like normal scan patterns are perfectly fine. For cryogenic experiments, we've seen, at least for samples that are not super beam sensitive or anything like that, that in fact the spiral is really helping us, and that was even a surprise to us. And for samples that are drift prone as well. So again, we were again surprised the spiral scan is really helping with this. And 40STEM, as I was just discussing as well, Mariana was showing for the barium titanate, really the direction very much matters. For dose fractionation, beam sensitive samples, at least we've seen, not in this presentation, but we've seen also with some sensitive polymer samples that Katrina within Imperial has seen that actually, in fact, jumping pixels has helped hers rather than these type of spiral scans. And then again, thinking about the damage decorrelation. So basically, in fact, maybe it's much better to do entirely random scan positions. And this again goes back to, do I want to see atoms, or am I trying to just basically collect STEM eels or something of a super beam sensitive sample? So just really, there is no perfect scan pattern. You need to think about what you're trying to get out from your data set. So again, the lesson is there's no universal best pattern. They all have very good advantages for many different materials. We can see that, in fact, we're getting surprised by how sometimes a spiral is being very good for us. And so that's why I guess the point of this webinar is for other people as well to try this out in different scan patterns and how that affects your materials, whether that is avoiding beam damage entirely, or perhaps you were also trying to move things under the electron beam. So the takeaways, we have our eels, because we were very excited, hopefully you can see this in the video, and we were very excited about how nice the data was coming out with the spiral scans, and how that really improved our actual eels resolution, and also for ptychography. So the takeaway is really scan pattern flexibility has really helped us for many different applications and many different material science questions we were trying to answer. It gives us alternative scan strategies, can really improve also the data quality, again, as Mariana has shown. And the programmable scan then enables new experiments. So for us, whether that's low dose ptychography or again, being driven domain manipulation for us, but also it can be many different for other researchers. It could be other types of cool manipulation of their material systems. And then the modern STEM, I guess, is moving beyond this raster scanning. We know this in our research field, whether that's material science or biological materials. Many research groups around the world and research centers, universities, and also independent companies are really focused on different types of raster scanning and how that can help basically improve the data that they are acquiring. And again, that's super important for very beam sensitive materials, specifically biological materials. So with that, I'd like to thanks again, Gatan, for the invite, and also I'm very happy to get to do this webinar with Stephanie and Mariana. And also thank you for bearing with us for changing slides, because unfortunately there's only one person that could present. So I'm sorry for some lag in the slide changes. Thank you.
Great, thanks so much to our speakers. If you have questions for them, we'll have some time right now to go through some of the questions that you may have. You can submit them through the questions pane, as we can see here on the slides. And we did get some questions for the team. So one of the questions I thought might be useful is for people who are new to ptychography or haven't done ptychography, is ptychography essentially a computational processing technique to improve the quality of the high resolution images that you are getting, rather than something that you can do by altering like the electron beam or the actual acquisition? That was one of the questions that we got. If you could just maybe give a little more context about how we can use ptychography.
I can take this question. So ptychography is an algorithm by which you're processing your 4D STEM data. So you're recovering these nice high signal to noise images in the end that contain information, for example, about your light elements. And these real space images that you're seeing reconstructed of this ptychographic data comes from the 4D STEM data itself. So it's a little bit different than, for example, just taking a 2D real space image and then applying some post-processing to that to get a nice image at the end. But the real space images you're seeing are coming from reconstructing of the 4D STEM data with these different types of phase retrieval approaches.
Yeah, thanks. We got a couple of questions also about the barium titanate that you showed. One question was, why are the oxygen atoms more visible in the spiral scan that you used on the barium titanate compared to the raster scan or some of the other scans? Is there some sample damage going on, or maybe some scan distortions? Do you have any thoughts on that?
Mariana, do you want to take that? Or
can you repeat that, please?
So in the images from the barium titanate that were collected, the oxygen atoms were more visible in the spiral scan. And the question is, what is causing the improvement in the visibility of the oxygen atoms, or a change essentially in the visibility of different atoms in the atomic columns across the images based on what scan you're using?
Yeah, so basically the resolution is improving because we're being able to resolve lighter elements, right, as is oxygen. So that means your phase reconstruction is better. So you're pushing your limits further with the continuous scan. And what we think this is happening, why we think this is happening is because when you have a continuous scan, your probe overlap has more of an even grid. So for ptychography, as Steph already explained, you just need enough probe overlap so that you can recover your phase information. But when you're doing raster, you get this line feedback, so you're scanning line by line. So that means there will be a little bit of a shift in every line or in your probe positions. So we think with the spiral scan, because it's continuous and there's no line by line, then you get a more even distribution, and that's why it's improved.
Thank you. Another question was about the idea, once you start using custom scans, do you ever have a concern in some of these experiments and looking at the domain walls where maybe you miss certain dynamics in parts of the area that are not being scanned?
Yeah, absolutely. So I think that's why we were basically trying to take so the The lucky thing is that it's cyclical. So when I showed like the 2D materials where you have a different atom and it's moving around, it's not entirely cyclical. Whereas in these materials, we know that if we keep going, if we go back to the original scan position, we can start from the start. So to remove that unknown, whether we're basically missing some information, right, at a pixel, because perhaps we're missing the dynamics, right? We're not either fast enough or anything like that. We can keep going back to the start, and we can keep changing those, whether that's the scan pattern direction, the rotation, how fast we're acquiring it, over and over again. And that's basically what we're working on at the moment. The ideal scenario is that we'd even go faster, right? Because I actually believe what's the thing that's only limiting us now is just really the speed of the acquisition. We can see that in certain scan directions, the domain wall itself clicks back. And so we're probably we're missing a movement. And we could see this before as well when we had basically a different camera, an older one, we are on our K2. We would see that basically from line to line that it would change the location instead of a continuous path, and you could see this kind of scan distortion. So certainly this is really what we're really trying to heavily work on. I think with the scan patterns, we can do so many things, but it's really the speed of our acquisition that's the only thing that's limiting us now.
Yeah, thanks. So there was a related question that came up of, do you think the K3 acquisition speed is required to be able to do these kinds of experiments? You kind of maybe just mentioned a little bit about that. Or another related question might be, what's the acquisition speed you ideally would like to have, you think, to be able to resolve these dynamics in these domain walls?
If I answer the last one as fast as possible, like hundreds of thousands of frames a second would be great. Because we can see, you can see in like if you use dynamic TEM and you weren't moving the walls with the STEM probe, you were moving it with an in situ biasing. Other groups have seen that in fact you can pick up very different things that are happening inside the walls as they're moving. And this is not just for electrics, it's other materials as well. So I think universally we just need faster cameras. And then the scan speeds that we're using, we're pushing it to the limit of the K3, but also we're going slower as well. So trying to basically calibrate a much slower acquisition versus as fast as we can push it on our camera, and then seeing again what kind of data that we are pulling out in terms of the domains, internal, the structure, the polarization, and also the wall itself.
Yeah, great. While we're talking about data acquisition, what was the microscope that you're using for the in situ experiments?
So we're using a Spectra 300 for all of the data shown here.
Great, thanks. One question that we got on the DPC experiments is whether you see any effect of the scan pattern that you use on the actual vector directions of the DPC.
I guess it's probably maybe the DPC I showed with the segmented detector, but so at that point we were only using rotating. I was only rotating the scan pattern itself, and it was much lower magnification DPC in that case. It's hard to disentangle what's real and what's not real, because the problem if you just use a segmented detector for your DPC and you don't use 4D STEM, you get a signal, a deflection of your electron beam due to the change in the tilt. And we know in these systems that different domains naturally are going to be tilted. So that's why we want to move to 4D STEM, because then if we take our 4D STEM data set, then we can get the DPC signal, but then also remove the change or the effect of the strain. But if we look at the 4D STEM and we just measure the polarization, then not just using DPC, but in fact actually measuring the polarization vector from that, we can see that inside the walls it becomes very messy, basically, the signal. And again, we're trying to now figure out whether that again is that we're in an in-between state and that the acquisition is just too slow. And so we're getting a mix of two different states. So you can imagine if a wall is moving at that pixel, perhaps we are getting data from, let's say, vector left versus up, because the acquisition is slower than the shift in the phase, or in fact that the phase itself is actually quite slow, the changing in the phase, because we know that in certain systems as well. That's kind of the next couple of years we're really trying to disentangle what's really happening there.
Great, thanks. We've been getting a lot of questions even during the question and answer segment. I don't think we'll be able to get them all, so I want to wrap up maybe just one more question about ptychography, and that's how should one choose a ptychography algorithm to use? Should they all show roughly equivalent results, or are there scenarios where one's preferable over the other?
I can maybe answer that question. So earlier in the presentation, I showed a bunch of phase retrieval techniques. I showed DPC, what I would call our direct ptychography methods, which includes tilt-corrected bright field, parallax, and SSB, and then also iterative ptychography methods. And in the order I just listed them, they sort of scale with computational demand. So DPC is great for doing sort of lab in situ experiments, while iterative ptychography takes a little bit longer and requires GPU accelerated resources. In general, we would like to see the results of these are going to depend a little bit on your sample and the way in which you took the data. All of them should yield phase retrieval results. If you're getting something very specific for just one reconstruction one time, that's very suspicious. So I would definitely think about checking your reconstruction parameters. But in general, also for iterative ptychography itself, there's different advantages to different methods. We want to try and converge something as physically realistic as possible. And I mentioned in the presentation earlier, these ML-based techniques that we have in Quantium specifically are a way for being able to improve resolution and depth sensitivity. So the base algorithm that I explained is the same, but depending on the exact reconstruction method and your sample, you might get slightly different results.
Great, thank you so much. I think that's all the time we have for questions. There were a couple ones that we didn't get to, so we will get to those questions over email. Keep an eye out for that. And thank you all again for tuning into the webinar today and for your participation.
Thank you.
Thanks.